Okay, so in this video, we're going to introduce how to find area enclosed by a polar curve. Okay, so to begin with, let's recall how we compute areas, or how we've been computing areas underneath curves when we were in Cartesian coordinates. Okay, so when we're in Cartesian coordinates, what we would do is we would write this as the definite integral from a to b of f of x dx, and here's our curve, y equals f of x. And when we integrate, what we're really doing is we're adding up a bunch of these little boxes. Okay, so the height of this box on both sides is going to be f of x, and our width is going to be that dx. Okay, but now if we're in polar form, our base unit that we want to find the area of is not going to be a rectangle anymore. It's going to be an arc, or going to be a wedge. Okay, so our base form that we're going to be finding the area of is going to be something that looks like this. Okay, so you can imagine this slice of pizza. So this right here is going to be theta. Okay, and if theta is small enough, the radius on both sides here is going to be the same. We can approximate it to actually be the same if theta is small enough. Okay, and the area enclosed by this region here is going to be 1/2 r squared theta, where theta is measured in radians. Okay, so what this means for us, if we're in polar form, and this, of course, is the pole. Okay, so if we have a curve traveling through polar space, or polar coordinates, we want to find the area enclosed in this wedge. What we can do is similar to what we did in with the tiny boxes, is you can just take a bunch of tiny wedges. We can find the area of each one of these tiny wedges. And by doing this, then we find the area of the entire curve, or the area enclosed by this region here. Okay, so our integral in polar form, so if we go from angle alpha to angle beta, our area enclosed by this is going to be the integral from alpha to beta of 1/2 r of theta squared d theta. Okay, and this is of course our function, which is r is a function of theta. Okay, so let's look at an example. We want to find the area enclosed by one loop of the four-leafed rose. Okay, that's r equals cosine of 2 theta. Okay, so r equals cosine of 2 theta. Okay, so this curve looks like this. There's our pole and our polar axis. Something that looks like this. Loops around like this. Loops around like this. Like this. And finally like this. Okay, so if your sketch is accurate, each one of these loops is going to be exactly the same, or petals or leaves are going to be exactly the same. So what I'm going to do is I want to find the area enclosed by this leaf here. Okay, so one thing that we want to be able to do is we want to be able to write this as a continuous interval of theta. Okay, so on this interval, our value for theta is going to go from from negative pi over 4 to pi over 4. Okay, so how do I know I go from negative pi over 4 to pi over 4 and not, say, 0 to 2 pi? Okay, so remember from previous videos, we saw that the period of this rows was 2 pi, and there's 4 leaves, so each petal should have should encase pi over 2. Okay, so if we're starting here at 0, we're starting halfway through the leaf, and if we go from 0 to 2 pi, what we're really getting is we're getting the top half here, and we're getting the left half over here is what we're actually enclosing. Okay, so be careful with your angles. Okay, so our area enclosed by this curve is going to be the integral from negative pi over 4 to pi over 4 of 1/2 cosine squared 2 theta d theta. Okay, so one of the things we can do is we can quickly pull out that 1/2. And then if you remember all the way back when we first started talking about integrals, when we talked about types of trig integrals, when we have cosine to an even power, we can use our half angle identity. So our half angle identity for cosine theta should be 1 plus cosine 2 theta, but we already have 2 theta, so this is 4 theta over 2 d theta. So the substitution is cosine, let me write it over here. We're using cosine squared theta is 1 plus cosine, maybe don't use theta, maybe call it x. One plus cosine 2x over 2. Okay, so we can pull out another 1/2 from the denominator here. So this is integral from negative pi over 4 to pi over 4, then 1 plus cosine 4 theta d theta. This is a basic antiderivative. So 1/4, this becomes theta plus sine 4 theta over 4. Evaluated at our endpoints, negative pi over 4 and pi over 4. Okay, so we keep the 1/4. Now we plug in our endpoints. So we should get pi over 4 plus sine 4 times pi over 4 over 4 minus negative pi over 4 plus sine 4 times negative pi over 4 over 4. Okay, we can simplify this a little bit. We know that this is really just sine of pi. Sine of pi is 0, so that term goes away. And this is going to be sine of negative pi. Sine of negative pi is the same as sine of pi, and that's also 0. So what we end up with is 1/4 times pi over 4 minus negative pi over 4 is plus pi over 4. So that's pi over 2 times 1/4, so we should get an area of pi over 8. Okay, and if you really want to double check that each one of these leaves has the same exact area, we can look at the area of the total curve. The area of the total curve would be 0 to 2 pi, should be the area enclosed by the entire curve, of 1/2 cosine squared 2 theta d theta, but this gives us 4 leaves. We only want 1 leaf, so we can divide by 4. And if you do this on your own, you should see that this is also then pi over 8. Okay, we'll come back and do another example. Thank you.